morning everyone. So, we will be start as you have seen in the last class that we are looking into the modeling of membrane modules, and we have looked into the very simplified version of the module modeling. We have considered the constant permeate flux that is coming out from the wall or from the membrane surface. Initially we have considered the flow through a rectangular geometry, which will be nothing but simulating the spiral wound module, and similarly we have looked into the tubular module, and although we have not derived the detailed equations for the tubular module, but this could have been done in the exactly the same way we have done for the overall material balance and solute balance and the pressure drop calculations in a in rectangular channel. So, modeling of membrane module indicates that we have to calculate the axial pressure drop that will be developing inside the membrane module, and this axial pressure drop calculation is very important in almost all chemical engineering applications, whether it will be a packed bed, whether it is a distillation column, or is adsorption column, or is absorption column, because once you know the pressure drop or flow through a pipe, so you whenever you know the pressure drop, then you will be able to know the rating of the pump by which the fluid has to be transported, so that the design of the pump or the in case of the liquid, or design of the compressor in case of the gas flow can be calculated easily if we know the pressure drop across the equipment. So, the selection of the driving agent, for example pump and compressor, is very essential to know the knowledge of the pressure drop in the process stream. So, that is why the pressure drop calculations are always very important in any chemical engineering applications, and so in our application as well in the membrane module. So, now we will be doing step by step, we will be adding step by step complication to the whole theoretical modeling as we have done earlier. Next analysis we will be doing that the permeate flux is not constant, it will be proportional to the transmembrane pressure drop, neglecting the osmotic pressure. So, we will be in the next analysis we will be doing the negligible osmotic pressure case, where permeate flux is proportional to the transmembrane pressure drop. In the third analysis and final analysis, we will be considering a case number 3, where osmotic pressure is not at all negligible, and we will be doing a real modeling of the membrane module. So, in this case 2, we will be considering the permeate flux is proportional to transmembrane pressure drop. We have negligible osmotic pressure of the solution. So, first we will be talking about the spiral wound module. So, as we have done earlier, that the governing equation of transmembrane pressure drop will be remaining same, that we will be assuming that the velocity profile is undisturbed by small permeation in the wall. So, the pressure drop profile, the governing equation for transmembrane pressure drop or axial pressure drop for delta p remains same, and this becomes, we have seen in the last class, that d square delta p dx square is equal to 3 mu h cube times V w, but in this case V w will be nothing but L p del p, okay, where L p is the membrane permeability. And the boundary conditions that we have already utilized earlier, one was the pressure drop in the at the inlet at x is equal to 0, this delta p is known to us, and also the flow rate is known to us at the inlet condition, and that will be at x equal to 0 d delta p dx is equal to minus 3 mu divided by 2 h cube w q in. So, since both the boundary conditions are specified on the same boundary located at x equal to 0, this is a typical Cauchy boundary condition, and we have already seen earlier that utilization of these two boundary conditions in the previous class. So, now this is a simple first order in second order ordinary differential equations. Two boundary conditions are specified. So, this problem can be solved quite easily, and I am just writing the solution directly, omitting a couple of steps in between. So, kindly do the derivation by yourself. So, delta p x divided by delta p in is equal to cos hyperbolic lambda x minus 3 by 2 mu q y h cube, this q in w lambda delta p in sin hyperbolic lambda x, where w is nothing but the channel width. Okay. And the parameter lambda is nothing but root over 3 mu L p divided by h cube. So, this is the expression of pressure drop at any distance x in the module or in the channel. Now, the axial pressure drop over the full length module length L becomes delta p I minus so this becomes delta p in minus delta p x is equal to delta p I 1 minus cos hyperbolic lambda x plus 3 by 2 mu q in divided by h cube w lambda sin hyperbolic lambda x, and for when x is equal to L, that will be give you the actual pressure drop in the across the channel. So, delta p in minus delta p L is equal to delta p in, this will be in 1 minus cos hyperbolic lambda L plus 3 by 2 mu q in h cube w lambda sin hyperbolic lambda L. Now, one can get an expression of fractional recovery of feed. The fractional recovery of feed over the entire module becomes F is equal to total flow rate in the permeate stream divided by total flow rate going into the system Q in. So, this will be nothing but 2 W V W dx over the entire length L divided by Q in. So, this will be nothing but 2 W L p 0 to L delta p x dx and divided by Q in, and we know the profile of delta p x. So, this can be inserted here and this can be integrated it out, and the final expression becomes 2 W L p delta p in divided by lambda Q in sin hyperbolic lambda L minus 3 mu q in divided by 2 h cube w lambda delta p in cos hyperbolic lambda L minus 1. So, we will be getting an expression of fractional feed recovery. So, we can also know, we can calculate the profile of permeate flux, because V w is equal to nothing but L p del p as a function of x. So, we can put the expression of delta p x and can get the permeate flux as a function of x if you really do that, the expression of permeate flux becomes LP delta P in cos hyperbolic lambda x minus 3 mu q in divided by 2 h cube w lambda delta P in sin hyperbolic lambda x. Now, the profile of V can be obtained, the profile of the retented velocity in the channel, that can also be obtained from this expression. So, if you remember that the governing equation of Q from the elemental mass balance, that we have already done in the last case in the previous class. So, elemental mass balance. So, basically mass balance over an element in the channel will give you minus dq dx is equal to 2 w v w, and in this case we have to put q is equal to 2 x h times u, where u is the velocity, u is the axial velocity in the channel. In channel, h is the height and 2x is the length. So, that will be the cross sectional area. So, we are going to get dq dx. Okay. So, now we will be getting, and Vw in this case will be Lp del p. So, du, you just substitute it over here. So, you will be getting du dx is equal to minus Vw over h, and we know the expression of Vw. Vw is nothing but minus Lp del p divided by h, where del p will be a function of x, and we have already calculated how profile of pressure drop varies along the x. So, we will be substituting that over here, and then you can integrate over u. So, if you really do that, so it will be nothing but minus Lp by h del p in by h, and then we integrate over we put the expression of delta p and integrate over 0 to x, and this will be from u in to u at any x location, will be giving you this expression 3 mu q in divided by 2 h cube w lambda delta p in sin hyperbolic lambda x minus cos hyperbolic lambda x dx. And if you really carry out the integration, the final expression will be nothing but u x divided by u in will be equal to 1 minus L p delta p in divided by h lambda u in sin hyperbolic lambda x minus 3 mu q in divided by 2 h cube w lambda delta p in cos hyperbolic lambda x minus 1. So, this will be a complicated equation, and if you really evaluate this will be a positive quantity. So, 1 minus some positive quantity, so it will be decreasing. So, as you go along the length, the velocity of the in the feed channel will decrease. Why the velocity will be in the feed channel will decrease? Simply because we are extracting some amount of material or in the permeate on both the walls. So, its velocity has to go down, and this is the expression of velocity in the flow channel as a function of module length. And then we can really calculate the concentration in the channel as well. So, assuming a completely retentive membrane, that means permeate concentration is 0. So, we will be having ddx of u c times 2 w h will be equal to 0. So, this is basically the solute mass balance over the differential length of the channel. So, therefore, u at inlet, C at inlet should be is equal to u at any x location, C at any x location. So, therefore, one can get an expression of C at x, C in is equal to u in divided by u x, and it will be inverse of that. So, we will be getting the profile of that 1 minus L p del p in divided by h lambda u I sin hyperbolic lambda x minus 3 mu q in divided by 2 h cube w lambda delta p in cos hyperbolic lambda x minus 1. So, therefore, the concentration in the fit channel will be increasing as a function of x, because the denominator will be decreasing as the length of the channel. So, inverse of that. So, therefore, the concentration will be increasing in the fit channel, and at the outlet the concentration can be obtained by putting x is equal to L, we can get concentration at the outlet of the module. And we have already got the expression of pressure drop, and from that we can get the rating of the pump, whatever is required, what wattage or kilowatt of pump is required to pump the fluid to overcome this pressure drop in the module. So, that gives a rough idea about the design of the module whenever we are talking about a rectangular channel, where when the permeate flux is proportional to the transmembrane pressure drop. So, next we will be carrying out an analysis for the, we will be putting out the results in the tubular module. We will be doing exactly the same thing, and finally will be, I will be writing the governing equations and the final solution of the tubular module. So, you just do the derivations following all the steps exactly the same way in the rectangular channel, then you will be getting the results in the tubular module. So, in case of tubular module, the velocity is given as r square, the cross sectional average velocity is given as u is equal to r square by 8 mu minus d delta p dx, and you will be getting the governing equation of d delta p dx is equal to 8 mu by r square times u. And if you do a differential mass balance, over a differential element will give you du dx is equal to minus 2 Vw by r. You can put minus 2 Lp del p divided by r, and similarly one will be getting an expression of, you can differentiate it once again and get du dx, substitute over here, combining these two equations, one will be getting the governing equation of d square delta p dx square is equal to 16 mu Lp over r cube times delta p, and the solution of this equation will be straightforward, and the solution will be delta p I cos hyperbolic mx minus beta sin hyperbolic mx, and m becomes a parameter which is nothing but 16 mu Lp over r cube. R is the radius of the tube, and beta is a parameter 8 mu u in divided by m r square. So, one can calculate the axial pressure drop as a function of channel length, tube length. The axial pressure drop becomes at any point, any location x, delta p in minus delta p x is equal to delta p in 1 minus cos hyperbolic mx plus beta sin hyperbolic mx, and one can get the axial pressure drop across the module. Module can be obtained by putting x is equal to L in the above expression. Okay. And similarly, the other parameters can be calculated. U over U I U in is equal to 1 minus 2 L P divided by M into R delta P in sin hyperbolic m x plus beta 1 minus cos hyperbolic m x. And you can get an expression of feed concentration, retention concentration as a function of C in is equal to U in by U x. It will be just reverse of this expression. So, this will be U in, and the denominator will be putting up this expression over here, and one can get. So, the axial pressure drop, one will be getting the idea is that the axial pressure drop will be varying as a function of x, and whenever we will be calculating the permeate flux V w L p delta p minus delta pi. So, delta p is no longer a constant. At every x location, the delta p will be varying as a function of x, and that will be taken care of, and one will be getting the axial pressure drop across the module, the permeate flux profile across the module, the velocity profile across the module, the concentration profile in the retented stream. So, once that is done, now let us look into a more and the most realistic case of the module, when we are not neglecting the osmotic pressure difference. So, we will be looking for case number 3 now, where we are talking about a Newtonian fluid, Newtonian steady state laminar and spiral wound module. Okay. So, the governing equation of transmembrane pressure drop remains the same. So, it becomes d delta p dx is equal to minus 3 mu q divided by 2 h cube w, and by putting q is equal to 2 w h u, this can be expressed in terms of velocity. So, d delta p dx becomes now minus 3 mu u divided by h square. Okay. The permeate flux V w is now no longer proportional to delta p. Now, we have L p del p minus del pi, and what is in terms of when we express pi is equal to b 1 c plus b 2 c square plus b 3 c cube, and we replace. So, delta pi is nothing but pi m minus pi p. So, pi evaluated at membrane surface concentration C m, and pi p is pi evaluated at membrane at permeate concentration C p. So, then we will be replacing R r in we will be replacing C p in terms of R r and C m. So, by defining R r is equal to 1 minus C p by C m, and we will be getting an expression of V w in terms of C m only, L p del p minus b 1 C m R r plus minus b 2 C m square 1 minus R r square minus b 3 C m cube 1 minus R r cube. So, this will be expression of permeate flux now there, and now we will be doing a solute mass balance in the differential area. If we do that, will be and if we do an overall material balance, then we will be doing a solute balance. So, doing an overall material balance in the channel in the elemental area, exactly like the previous cases, we will be getting du dx is equal to minus V w by h. So, this will be the governing equation of u in the channel, and V w is nothing but L p del p minus del pi. So, what is the, then we do a solute mass balance in elemental area. In this case, this becomes duc dx becomes minus VW Cp divided by H. H is the half height of the channel, Cp is the permeate concentration, and you just open it up the left hand side, it becomes U dc dx plus C du dx is equal to minus VW Cp over H. Then we can replace du dx from this equation here, and ultimately you will be getting the governing equation of dc governing equation of concentration. So, this becomes VW by H C minus Cp. So, this will be the governing equation of transmembrane pressure drop or axial pressure drop. This will be the governing equation for permeate flux. This will be the governing equation for velocity. This will be the governing equation for concentration in the feed channel. So, I will be having 3 ordinary differential equations for accounting transmembrane pressure drop, velocity in the retentive channel, as well as the concentration in the retentive channel. So, 3 ordinary differential equations for delta P, U and C in channel or module, and they will be having the conditions. We know the boundary conditions on delta P at x is equal to 0. So, at x equal to 0, we have 2 boundary conditions on delta P. Delta P is equal to delta P in, and another one over the related the U in d delta P dx, that will be known to us. At x equal to 0, U is equal to U in, and at x equal to 0, C is equal to C in. So, these will be coupled, but Cm is still not known. So, for that, what we are going to do next is we do a we relate the bulk concentration with the membrane surface concentration. So, we have to relate Cm to C. So, this is bulk concentration, this is the membrane surface concentration, and C is the bulk concentration. How these are related? These are related through the mass transfer coefficient. So, for every x in the module, for every x location in the module, we have this relation holds good, k Cm minus C is equal to minus d del C del y at y equal to 0. Okay. So, this is the definition of mass transfer coefficient that is valid at every location, and at steady state we have seen earlier also sum of all fluxes towards membrane equal to 0. So, if you do that, this becomes VW Cm minus Cp is equal to minus d del C del y at y equal to 0. Therefore, we can equate these two and we will be getting k Cm minus C is equal to VW Cm minus Cp. This can be replaced, VW Cm minus Cp can be replaced in terms of real retention. So, this becomes VW Cm RR. Okay. Now, we will be getting this algebraic equation to be solved at every step. So, then we will be what we will be doing, we will be putting the expression of permeate flux here as Lp into delta P minus delta pi, and we will be expressing delta pi in terms of Cm, and let us see what we get. So, by doing that, one will get k Cm minus C Cm RR, and VW will be Lp del P minus delta pi k Cm minus C is equal to Cm RR Lp, and this will be delta P minus A1 Cm plus A2 Cm square plus A3 Cm cube, or k Cm minus C divided by Cm RR Lp is equal to delta P minus A1 Cm plus A2 Cm square plus A3 Cm cube and the constants A1 are related to original osmotic coefficients and real retention. So, A2 is equal to B2 1 minus RR square of that, then A3 is equal to B3 1 minus RR cube of that. So, now we have to find out what is the expression. So, this algebraic expression has to be solved. Also, k is a function of x, as we have seen earlier, that k of x is equal to 1 over I u d square by h x to the power 1 upon 3. If you remember the mass transfer coefficient analysis for the flow through a rectangular channel. So, what I will be doing now, I will be stopping here in this class. In the next class, I will be hooking up mass transfer coefficient as a function of x and writing the complete solution, complete expression of the algebraic equation that has to be solved at every step of 3 governing equations of delta p, u and c, and then we will be seeing how the module design can be done in a very complicated and realistic case. Thank you very much.